Anyone know any jokes? Start? Okay. Good morning, everyone. Welcome to day number 3 of 4 sets. Today I'd like to start by just reminding you of kind of two things that we've seen that have been important that I've emphasized with fluids. First of all, the conservation, the fact that conservation laws form a fundamental part of the fluid model from the very beginning. And that's going to be important because we want to develop numerical methods that also satisfy the same conservation laws. So they're integral in the way the fluid model is developed, and they're going to be important for our numerical methods as well. The second thing is the fact that there are shocks or discontinuity that generally form in the solution. When I have fluid flow that's dynamic, and in astrophysics this is a regular occurrence, we have shocks. And as you saw yesterday in the tutorial, if we use kind of the standard numerical methods, they don't work very well with the shock, right? We had problems even with our linear equation. And if the equation were nonlinear in addition, then those nonlinear, those oscillations and those kind of spiky stuff that we saw would grow and it would completely contaminate the solution. So we're going to kind of focus on these two things as we develop numerical methods that we can use more generally. Okay, let's look at conservation first. We've kind of done this before, but just to remind ourselves, I'm going to assume I have some quantity Q that's conserved, and I'm going to now work only in one dimension. So before I've always talked about generic arbitrary volumes. Now I'm going to start thinking about doing this in one dimension with a numerical method. And so I'm going to kind of specialize here and just imagine I've got, say, some box in one dimension, along one dimension, and I have fluid in there or something in there. And I can define a density such that the total quantity of whatever this conserved quantity is at a given time is an integral from, we'll call it x1 to x2 of little q xt dx. So I've got an x1 and a x2, and I'm integrating over that line, that portion of the line. Okay? If I want to know how q varies in time inside of the box, then I can write that as, well, of course, I can take the time derivative of my integral, which I've just written down. And I'm going to write that as in terms of function f like that, where this function f is a flux function. And you've seen this before. You kind of know how to interpret this. This tells me the total quantity Q that's in my box can change in time if I have a flux. Oops, I wrote these with U's. Let me meant Q, sorry. If I have a flux of Q that comes into the right, it will increase. And if I have a flux Q that is moving to the right out of the box, or this way to the right, then it leaves the box, and so I have the minus sign there. So that's my flux function, okay? If I want to, I could write a formal solution to this problem by simply integrating in time. Now, when I say formal solution, that means I can write down mathematically what the solution will look like. It just means I can't really solve it yet. But I could imagine just coming here and just integrating from time 1 to time 2. With a dt, and same over here. Let's make those square brackets. And we have a dt. And if I integrate that in time, because I have a total time differential here, this would be simply q at x, x t2 dt minus q of x t1 dt, x, thinking always ahead here. And then I need to integrate these two functions in time, and so on the right-hand side, I have now an integral in time of this function here. Okay, I guess that's a formal solution. Yeah, that is the answer. We just don't know how to evaluate it yet. The important thing that will come out here is that these integrals, these integrals of the flux functions are integrals at constant position. Okay, and we're going to exploit that fact later on. Now, I'm not going to do this on the board, but you can show that if, for example, at this stage here, I could write this as the integral of a total differential of an x. And I could say that if f and q are smooth functions, I can exchange the order of integration and differentiation. And you could quickly show that this conservation law and the form that I wrote down here reduces in integral form to this, which is what we've been seeing before. So it does do that. Now, as I said, we want to build numerical methods that satisfy the same integral conservation law. This is how we'll do it. Instead of defining like the density here, what I'm going to do is define an average value of q. Okay, so I'm going to say that if I have a function q, and I'm trying to, well, let me back up a little bit and say this. Let's say that we have a function q that is a solution to an equation maybe like this one. And I want to find what q is. If we were doing finite differences, what we usually imagine is this. Take a discrete grid of points in, say, x, and I maybe label them xi plus 1, and so on like this. Take these discrete points and approximate the derivatives that appear here and here with finite difference operators, right? That's what we did. And what you did with Sasha and on the tutorial yesterday, the upwind method, we just approximated with finite difference operators these things. Now, when I write down an approximate derivative, and maybe I'd say that the derivative in x of q is approximately equal to q at I plus 1 minus q at I over delta x. When I write that down, what I'm assuming is that you take the value of q at this single point and subtract it from the value of q at that single point, divide by the distance between them, and that it's my approximate to the derivative, right? That's what we mean by finite difference. What we're going to do now, because we're worried about conservation, is we're going to do something different. It will look the same in simple cases, but it's fundamentally a different technique. And we're going to look at a finite volume discretization instead. Because my conservation laws in integral form are integrals over a volume and not just evaluating the function at a single point. So we're going to build our numerical methods in the same way. This is how we'll do it. Imagine I've got my function q now. It looks like this. Okay? Instead of just taking the value at one point, I'm going to take my grid, and I'm going to imagine instead of just discrete points, I have cells. And the center of a cell is that on a grid point. And what I'm going to do is I'm going to define the average value of q over this cell. Now, this is the point I plus 1. This is the point I. I will call this midpoint I plus a half. And this midpoint will be I minus a half, and so on. And so what we will do is we'll define the average value of q in the cell, and I'll write it as capital Q like we had before. And I'll say that the average value between x at I minus a half and x at I plus a half is the integral of the little function q x of t dx, like that. Exactly the type of thing that I wrote down before for the continuum case, except I'm going to do one more thing. I'm going to put in I'm going to divide by the grids, by this length of the cell. I'm going to assume for simplicity that the cells are uniformly sized. They're the same everywhere. It doesn't have to be. It just complicates your life if you change it. Okay, so now I have an average value. Now, because I'm going to work with solutions that are discrete both in space and time, let's go ahead and we'll put an n index there to indicate that this is evaluated. This integral is not the spatial integral, and we'll evaluate it at time n. And I'll put an I down here to remind myself that this is the integral over the cell centered at x point I. Okay? Now, I want to know how the quantity q, the average value of the function in this volume, changes in time. Well, the same thing that we've seen before. I'm going to have a flux that depends on q, which is a function of x and t. And this is at x1, and a flux at x2, like that. So exactly what I wrote down in the continuum case over here. Now, my fluxes aren't discrete things yet, right? There's still some flux function, and I wrote it explicitly as little x and t because I haven't made that discrete yet. But what I will do is this. I'll say, let's integrate this in time. From Tn to Tn plus 1, like that. When I integrate, this is a total differential in time, so when I integrate in time, I'm going to get Qn plus 1 I minus Qni, like that, right? Because it's just a total differential here. Then on the right-hand side, oops, what did I do wrong? I'm missing a delta x. I'm missing a delta x because I needed to divide this by delta x. Why did I have to divide that by delta x? Because my q here I defined differently from the continuum case with an extra delta x in the denominator. So when I wrote down the flux, I need to have this delta x in the denominator as well. So the difference is in this case, q here is a density. It has units of whatever capital Q has divided by length. In this case, they have the same units, right? So there's my delta x. I integrate this in time. I'm going to have a 1 over delta x. And I have now these integrals of this. And let me not write all of them down. Let me just go ahead and define what I'm going to do here. What I'm going to do is take this integral of f of q at x1 t dt from Tn to Tn plus 1. I'm going to divide by a delta t, and I'm going to define this to be a numerical flux function. And this is the numerical flux function, so if this is evaluated xi plus a half, then I'll call that the numerical flux at xi plus a half. So I'm taking that integral, and I'm writing it as now a new function, capital F. I've put a delta t in here, an extra delta t. So if I make all of this the same, I've got to put a delta t in the numerator here, a delta x. And that's my integral form for a finite volume discretization. I'm writing the capital F here with a script type f so that it looks different than this one. Because we have to remember that this is a numerical flux function, and it's not necessarily just what f is in the continuum problem. It's something else, perhaps. And it usually is. Okay, so this is my numerical flux. And this will be my conservation law. Now, over here we could easily convince ourselves that this was a conservation law and Q was conserved. Can you imagine that this discrete capital Q is also conserved on my grid? How could we show that that really is true? How would I know if capital Q really is conserved? I imagine I set some function here, maybe this is a fluid, and we let it evolve in time, and it shocks, it moves around, it's dynamic. How could I show that it really maintains discretely a conservation law? Yeah, it looks like a continuity equation. I could come back up to here, and I could imagine, well, let's consider some group of cells. I could say, how does the function change here? Equivalently, this is the cell average for a single cell, right? At one time, this is the cell average at another time. What I could do is I could just add up the cell averages at one time and compare them to the cell averages at another time, right? So let's do that. Let's say, I don't know how to index this, but let's say that we imagine some big part of our grid, and we'll just say that we start at index J, which is way over here, and we end at some index K, which is way over on the right. And we say, well, if I want to add up the total average value of this function over the entire grid, that's just the capital Q's. If I do that at one time, then I would just add up from some index J to some index K, and it could be as big as I want. That would be equal to, if I use this, if I just sum this equation here, that would be equal to the same sum at the previous time. And then I have to figure out what this guy does. I've got a delta t, a delta x, and I'm going to sum in the same manner from j to k. And I'm going to add all these guys up. What happens is I add up this difference for the point I plus 1, the point I plus 2, and so on. You see what's going to happen? The flux functions on the left at neighboring points are going to cancel out. And the only flux functions that will remain are the flux functions on the extreme ends. The flux function at j minus a half, the flux function at k plus a half. And that is exactly, so this sum here that we would write down would all collapse, and we'll just be left with that one. And this is a k, and this is a j minus a half. Yeah, I messed the sign there. Sorry, that should be a minus sign. And I have the reason it's a minus sign, see here this is x1, this is the point to the left. This is the point to the right, x2. But here I change the order on you, and this is I plus 1 is to the right, and I minus a half is to the left. So I forgot to put the minus sign right there. Okay, so it really is true that this, if I integrate over my grid, I have conservation. Let me show you what happens if you don't have conservation. So yesterday we looked at Berger's equation. We wrote it two different ways. That's Berger's equation in flux conservative form, right? Because I've got a flux function 1/2 u squared. Take the derivative of it, and that's looks exactly like this one over here. I could also write it in non-conservative form, and it was that. So I'm not going to take the time today, but imagine now doing the same process with this equation. When I do the integrals, define the averages, and sum them all up, these terms will not cancel out, because when I write a finite difference for this, it might look like this. with a delta t and a delta x here. Okay. This is, if you look at this, what I'm doing is upwind method, right? We saw that worked pretty well for the advection equation. And I just put an extra factor of u in here. Now, when you take this term here and you add it for neighboring points, the fact that this here is not symmetric with those means that those terms will not cancel out. And if you do a finite difference of this, it will not be conservative. And it will, anyway, be bad. We'll see that non-conservative discretizations give you the wrong solutions for shocks. Okay, so that's the idea behind doing a finite volume discretization rather than a finite difference discretization. Okay, so that's conservation laws. The next thing I want to talk about are discontinuities. We saw discontinuities. We know our fluid equations are going to have discontinuities. We need to figure out how to handle them. What we want to do is kind of, again, step back a little bit and study what we can learn and understand about discontinuities that appear in solutions. Again, I'm thinking of Berger's equation as an example. If I want to imagine the simplest solution that has a discontinuity, it's called the Riemann problem. The Riemann problem is an initial value problem where I have it's a one-dimensional problem, and I have say at x equals 0 or something, I have some type of a division, and on one side of this line I have one constant value of the solution, and on the other side of the line I have a different constant value of the solution, so that I begin with an initial discontinuity. And then I imagine that I evolve this data forward in time. When I do this with fluids, there are things called blast wave solutions. And basically you do this in the lab with a big tube. You put in some type of foil in the middle of the tube. You put gas on either side, and you can change the pressure or the temperature from one side to the other. And then you have some mechanism to puncture the foil, and then shock waves or refraction waves will travel down the tube. And that's the experimental form of this type of problem. Okay? So this is what we're going to think about solving. The solution for Berger's equation for this problem is fairly simple. So I'm going to call this the right state. I'll just call this UR. And I'll call this the left state UL. Okay? There are two cases, basically. If U left is bigger than U right, and assuming that U is positive so that the waves travel to the right, then there is a solution to Berger's equation, and it is this. I'm sorry, there's a solution to the Riemann problem, which is U of x and t is equal to U left if x is bigger than s times t, and U right, have I got those backwards? If x is less than s times t, where s is 1/2 UL plus UR, U right. Okay? So what is this? This is basically a shock wave. So again, my initial state here is at time, t equals 0, x equals 0, I've got U left here, and I've got U right here. Okay. U left is larger than U right, and so I have a shock wave that now in time propagates with velocity s to the right. So that if s is, oh, I did these backwards, didn't I? I thought I would do them anyway. I thought they looked wrong. If x is less than s times t, so the shock wave position of the shock is s times t. If I'm less than that, I get U left. If I'm greater than that, I get U right. Okay? So that's one solution to the Riemann problem in Berger's, for Berger's equation. By the way, I just mentioned this. This problem has independent of scale, right? I have a single discontinuity. The solution is constant on either side. So if I change the scale of the problem, nothing changes, right? Since this has this symmetry, the solutions are what are called self-similar. You'll see that as we go on. They're self-similar solutions. Okay. Well, Berger's equation is simple enough that we have only one other case to consider. I don't want to erase that.
How we are defining this thing, I'm not understanding.
How do we define the S or
The function.
the function?
Yeah, u of x.
U of st?
Yeah, u of x. How we are defining it.
So u of xt, if x is less than s times t, then it's simply ul. And if it's greater than that, it's simply ur. So that this is a shock wave. This solution doesn't change its character. If it looks like this initially, then the shock wave simply propagates with velocity s. Does that make sense?
Is U the solution of the Berger equation?
Yes, U is a solution to Berger's equation.
A shock kind of a solution, or discontinuous solution.
So I'm beginning with discontinuous initial data like this. This is case number 1 where U left is bigger than U right. The speed of propagation is to the right. And when I have this discontinuous initial data, this discontinuity, this shock, will propagate to the right at a given speed given by this. The height of this is UL, the height of this is UR. So that's the value of U that's in Berger's equation.
Similar to the yesterday which you gave the numerical problem with a discontinuous function.
Could you say that again?
A problem with a discontinuous function as initial condition.
Yes.
And how it propagated with time.
Yes.
Similar to that kind of.
Yeah, so yesterday you worked only with the advection equation, right? So in Berger's equation, this is Berger's equation. If we remove the 1/2 in the 2 here, then that's the advection equation. That's what you worked with yesterday, was just the advection equation. But we did use discontinuous solutions like this. So the second case is that U right is bigger than U left, right? So this is initial data that looks like this. Okay, at the initial time. In this case, now remember, I'm assuming that the U's are positive here. In this case, that means, if we go back to this form here, if the U's are all positive, this tells me that the local characteristic velocity, if I interpret that U as this local characteristic velocity, is to the right. In this case, this solution is also a solution. This discontinuity, we could imagine this discontinuity simply propagating to the right with velocity s. Turns out that that solution is unstable to perturbations. Okay? It also, if it were a fluid, would violate entropy. I'll show you that in a moment. But there is a different solution that is stable, and that's the one that we're interested in, which is called a refraction. And what happens is this initial step function starts to move over and become a solution that looks like this. Okay? And this is called a refraction wave. And the solution here is, for case 2, the refraction. The solution Ux of t is, and here I have to make sure I get these written down right, so I'll look at my notes. It is UL if x over t is less than UL. It is x over t if UL is less than x over t less than u right, and it is UR if x over t is bigger than UR. Okay? Let me talk a little bit about how we can think of these solutions, and that's by looking at their characteristics. Do you remember the characteristic velocity for Berger's equation? It was simply u, right? In the case here where UL is bigger than UR, so my initial data for the Berger's problem looks like this. The characteristic velocities, x over t, are equal to u. Now, if I think of this as being time and this being space, then I'm going to plot 1 over the velocity, right? So this is a small velocity, 1 over a small velocity is something big, so these are fairly steep slopes. Those are the characteristics here. This is going to have a more curved slope, like that. Okay, those are the characteristic directions. What happens when these cross? I have a discontinuity, right? A shock. And if I look in time at how that discontinuity propagates, if I imagine it propagating like this, on the right to the front of the shock, I have characteristics that look like this, and on the left, they look like that. And I see that all the way along, characteristics meet at the shock, at the discontinuity. And that's a physical thing that's allowed to happen. If I go to the other case that looked like this, and I now imagine that I just have the shock solution, and I say this discontinuity propagates with velocity, s. Now this is what we would expect from the advection equation, right? When you put this type of data into the advection equation, the whole thing just moved along at the same speed. That's because in the advection equation, the characteristics are always constant. In this case, however, the characteristics look like this. So the shock is moving like that, and I have characteristics on the right that look like this, and characteristics on the left that look like that. I have characteristics that are emerging from the shock, and that's something that's unphysical. And so this is a solution is not physical. If I look at the refraction solution, in this case, I have characteristics for this problem that look like this. And on the left, they look like that. Oops, not backwards, but more straight up. And in between, I have this. It's the solution is simply x over t. Those are simply the lines that are going to go like this, that go in between those. So I have to draw that one there. They're the lines that look like that. So I've drawn that on top of something. Let me make it a little more clear over here. I basically have characteristics on one side that look like this, characteristics on the other side that look like that. And the refraction fan, it's called a fan because the characteristics in between have this fan shape like that. And so those are the characteristics. They're all emanating from a point, nothing coming out of a shock or discontinuity. And so that's a physical solution. So those are the two types of waves that we expect when we have discontinuities. We expect to see shocks. We expect to see refractions. There's a third type in the Euler equations called a contact discontinuity. I think now I'm going to set the projector up for a moment. And let me just, while I'm doing this, if I can talk and do this at the same time. Maybe I can't. The nonlinear waves, sometimes they're called the nonlinear waves in a Riemann problem. There's a third type of wave. If you recall to yesterday, we've mentioned, or I mentioned that in the fluid problem itself, there were 5 eigenvalues if you look at the characteristic problem for the fluid. 2 of the eigenvalues looked like, in Newtonian physics, the velocity of the fluid plus or minus the sound speed. Those 2 characteristic velocities correspond to the nonlinear waves. They are shocks or refractions. The other 3 eigenvalues were all degenerate. They were the same value. They were the velocity of the fluid. These 3 eigenvalues are not nonlinear, and they give rise to a third type of wave that's in the Riemann problem, and it is called a contact discontinuity. And a contact discontinuity, because the eigenvalues are degenerate, the contact discontinuity has eigenvalues or characteristics that are parallel on both sides. So in the fluid problem, we actually have all 3 types. We have 2 nonlinear waves that could be shocks or refractions, and then we will always have 1 contact discontinuity where the characteristics are parallel to it on both sides. Okay? So, this is the Riemann problem for relativistic fluids. Okay? This is a problem done in special relativity Cartesian coordinates, right? Because there's no geometry, it's just flat geometry here. I could write my fluid equations in this form where U is a vector of density, momentum, energy. Okay, so there are 5 variables in here, 3 components of momentum and energy and a mass density. Again, I'm doing this where I have 1 state on the left, 1 state at the right at the initial time. The solutions are either going to be shocks if the characteristics converge, refraction waves if the characteristics diverge, or a contact discontinuity if they look like this. The way, kind of the traditional way of labeling things is you kind of draw a picture like this. This represents my horizontal, my spatial axis. The vertical axis is time. The initial discontinuity is here. On the left, I have a state specified by the density, the velocity, and the pressure. And on the right, I have the same. So I have an L or an R to distinguish between left and right. The 2 nonlinear waves are the red of the blue line. These are the waves that propagate either velocity plus or minus c. They're the fastest waves that are on the outside. Behind the nonlinear waves, I have these states indicated by a star. So this is the left star state. That means it's on the left behind the nonlinear wave, and this is on the right behind the nonlinear wave. The green line indicates a contact discontinuity. Now, I've drawn them kind of spread out like this, but they don't have to be. I mean, they can all be tipped to the right or all tipped to the left, or anything's possible. Notice that I have an L and an R for the density, but there's no L or R on the velocity or pressure. That's because across a contact discontinuity, only the density can change value. The pressure and the velocity are constant. And to understand that more, you have to go through the entire analysis, but I'll just give that as a fact, or as by way of explanation. We've said that. Okay. So this is kind of a graphical way of how you solve the Riemann problem. You basically write down equations like this for S that show you how fast a shock can propagate. I'll show you in a moment how to do that in more general. You also have equations that tell you how to work with the refraction wave. And basically what you do is you imagine that I start with the initial states A and B. Now, as I said, the pressure and the velocity are constant behind the nonlinear waves. The density can change depending on where the contact because of the contact discontinuity. And so because behind the nonlinear waves, pressure and velocity are constant, you work in this pressure velocity, plane, and you plot your initial 2 states, A and B, and then you connect all the states that can be with a right-moving refraction wave or right-moving shock that go through state B on the right. On state A is on the left, and I find all the states that I connect with a shock or refraction wave. Where these two lines cross, that is the solution. That is the solution for the star state that's behind the nonlinear waves. So these are two examples. Let me show you what's plotted here. These are examples of the relativistic fluid, the Riemann problem for the relativistic fluid equations. Okay. The initial discontinuity was here 1/2. On the left, the state was given by these straight lines here, so the initial velocity was 0. This is the density divided by 10, so on the left, the initial density was 10. The initial pressure was something 25 or 20, I can't remember. Or anyway, this is pressure divided by 20. And then on the right-hand side, this is the initial right state. What happened is I had a shock that propagated from the midpoint to the right. Okay, so if I look at my shock, I see the velocity is the red line. I have this discontinuity in both the velocity and in everything, right? Because pressure is the blue line. There's a discontinuity there. You just can't see it. And the green line, there's a discontinuity here. This is the right-moving shock wave. On the left-hand side, you don't see anything is a discontinuity. This part right here, where the velocity changes smoothly from one value to another, is the refraction wave. And the pressure changes smoothly, the density changes smoothly. This state right here, in between where the refraction wave ends and the shock, this is the state behind the nonlinear wave. Can you identify where the contact discontinuity is? It's right here, right? This is the contact discontinuity where only the density is discontinuous, but the pressure, the blue line, and the velocity are constant between the refraction wave and the shock. Okay? So that kind of shows you, I wish I had a movie showing you this in time, but I didn't have time to do that. Now, with relativistic fluids, we can get very narrow shocks. And so in this case, the initial pressure was 1,000 on the left-hand side, and on the right-hand side, it was 0.01. And the initial velocity was 0, and the density was 1 all the way across. And here we see the same features. I've got a huge refraction fan, but you notice how narrow my shock is now in this contact discontinuity. So with relativity, again, because you have Lorentz and you have contraction effects, these things get pushed can be very small. Anyway, so that's an example of a case where I have a shock moving to the right and refraction waves moving to the left. Of course, you don't have to have that. You can have solutions where you have shocks everywhere. Here I have a left-moving shock and a right-moving shock, and a contact discontinuity in between. How do you think I get shock waves going both ways? You basically have the fluid, you give the fluid on both sides a velocity towards the initial discontinuity, and then you get a propagating shocks outward. Or if I have the fluid traveling away from each other from the initial state, then I can have a refraction waves on both sides. And here I can say I have a small refraction fan, a little bit bigger refraction fan, and this big constant state in between with the contact discontinuity right there, the green line. So those are what the solutions to the Riemann problem in relativistic fluids look like. Okay? We will use these solutions now, so I have references there, to work on numerical methods. And this is probably a good time to take a break, because when we come back, we're going to use this Riemann problem to design a numerical scheme. With Berger's equation. And you can see that I started off with values of u that are positive. The value on the left was smaller than the value on the right. And instead of having just a discontinuity that propagates like this, I have this refraction type fan, and this is the refraction wave right here. And I can run it longer and it can go off the grid. So in this case, now if I add up the amount of U on the grid, it's always decreasing because I have a flux on the outer boundary where it's leaving the grid. U is the, I'm sorry, so this is the spatial axis X, this is U on the vertical axis. Okay? We can look at a case with both a refraction and a shock. So this will be a stair-step solution initially. And for this, here I have a discontinuity because I have a higher value of U here than what's in front. So I have a shock moving to the right and a refraction fan again on the left. Okay, so there's an example where we see both waves at once. And I think that's probably good for now. So I'm not going to need that for a minute, I don't think. I'm going to go ahead and turn the projector off and raise the screen. And in the Berger's equation, I just told you that this was the speed that the shock would travel at, the average value between the left and the right. That probably kind of makes sense, but I want to show you how that's calculated because the same type of calculation is used for the fluid equations, even though they're more complicated. If we think about our conservation law here, what we wrote down at the beginning, I'm going to simplify the notation a little bit. So rather than writing f of u of x and t, and I'm just going to say that this is f at the left boundary and this is f at the right boundary, and I'm integrating from, say, minus m to plus m. I'm going to assume the discontinuity is initially at the origin. Okay, so I have a picture like this. This is the initial position, x equals 0, and I'm integrating to x equals plus m and x from minus m to plus m like that. Okay, and I know that, and I'm going to put m so far away that the shock wave has not reached the end of my volume yet. So m can be far, far away. It can be big. Okay? Now what I want to do is I have this equation here that's the conservation equation. I can also just go ahead and evaluate that integral because it's actually not hard, right? That integral, so I assumed that at time t, this is the solution. It's traveling at some velocity s. I'm going to say I don't know what that is yet. And if I were to now do this integral, I would say that this would be simply equal to, so this distance here is m, this distance here is s times t, and so this is simply m plus s times t times whatever the value is on the left, plus m minus st, so that's the final distance right there, times whatever u is on the right. Right? When we have these nice constant functions, it's easy to do these integrals. Now, I can actually go ahead and just differentiate this integral, right? I need the time derivative of the integral up here. I can actually just go ahead and differentiate this result immediately, and I can see that if I take that time derivative of this integral, that is simply going to be ul minus ur times s. And from the top equation, that is equal to f of ul minus f of ur. And now we solve for s. And I have that. And that's actually how I solve for what the velocity of the shock will be. And you'll see this in books often written this way. They'll write a square bracket around the f and a square bracket around the u, and that means that right and left difference. Now when I do this for the fluid equations, remember I showed you when you solve the shock tube problem, or the Riemann problem for the relativistic fluids, you have all these states that you connect with shocks. Basically what you do, one of those equations that you solve in that graphical solution is this one right here. You find all the states that, and you find the shock speed, and you have to make, anyway, you go through that process. That's one part of solving the Riemann problem for a shock. Okay? So that's where that comes from. Now I want to show you a complication that arises. I don't know if you remember, but yesterday when we talked about weak solutions, I mentioned that they're not unique. And I can show you quickly an example of that. So this is Berger's equation. Right, that's Berger's equation. Now, if we had nice classical solutions to a PDE, meaning that they're continuous and they're smooth, no discontinuities, then you would know that if I transform variables, the solution should be the same, right? And so I'm going to go ahead and multiply this equation by 2u. So that looks like this. If I now rewrite this a little bit, I could rewrite this as the time derivative of u squared. Right? That would give me 2u times the time derivative of u. And then I come to this equation, and it looks like I want to, if I take this derivative, I'm going to get a 2u squared. That 2 cancels that one. And I'm going to have, I want 2/3 u cubed x, I think is the right thing there, right? Those are the same. So this is just a transformation. And again, if we had classical solutions that were smooth and continuous and differentiable, this should have the same solution as that one, right? Now, we just showed you how to find the shock speeds. Let's assume, now let's calculate the shock speeds for both cases. Call this equation 1, this equation 2, whatever. So the shock speed for number 1 would be f of u left squared with a 1/2 minus f of u right. I'm sorry, I'm doing writing something incorrect here. So shock speed number 1 is the flux on the left side minus the flux on the right side, which is 1/2 ul squared minus 1/2 u right squared. Then the denominator is the solution on the left minus the solution on the right, like this. And this is going to be ul plus ur, right? Which is exactly what we had written down, because this is a difference of squares, and there's, anyway, it can be written as that term times that term. Okay, if we calculate now the shock speed for number 2, the same one thing. I got 2/3 u cubed left minus 2/3 u right cubed over u left squared minus u right squared. This is not equal to S1. And so by changing this, if we look at the weak solutions, just by transforming the problem, we got the wrong solution. We got a shock speed that is not correct. So this is an example of the case where there can be more than one weak solution that's available. The way that you find the physically correct weak solution is, first of all, you keep your equations in the proper conservation form that they originally derived in, and then you look at the solution that exists in the limit of vanishing viscosity. It's the vanishing viscosity solution. And if Berger's equation, the first time I wrote it up there, remember I had on the right-hand side a little epsilon times a second derivative of u, a dissipation term. And then when I wrote it up there, then I kind of threw it away and said we'd use the inviscid Berger's equation. And the limit that epsilon goes to 0, then I get, if I calculate that for non-zero epsilon and let epsilon get smaller and smaller and smaller, that's how I identify the proper solution. And the other way I can tell is that there are entropy conditions. And we don't have time to go into that, so I'll just tell you, if you want to know more, you have to figure out some way to measure entropy in your solution and make sure that it always increases. And a shock that moves to the right in Berger's equation is, well, anyway, case 2, if it's a shock, it violates entropy conditions. But we are marching on because time is short. Okay. Yesterday, when you did the tutorial, you found, remember, that the upwind method worked the best for our advection equation, right? So in the advection equation, the velocity was such that the wave always propagated to the right. So we were solving dtu plus dxu equals 0. We put on some function here, and the characteristics are constants, and so this just moves to the right, correct? And you found that if I made that discontinuous or had sharp features, that the upwind method did best, and the numerical solution looked kind of like that. I kind of smeared it out, but otherwise I did okay. The reason the upwind method works well is because the way we wrote it down like this. If I were to imagine the discrete points, so this is space, this is time, this is the solution at time n, this is the solution at time n plus 1. Okay. If I look at this, this tells me, and this is point I, say right here, the solution at point I at time n plus 1, so that's this point right here, is equal to the solution at the same point, but at the previous time, that's that point. And then I have some combination here where I'm using the same point, and then I'm using its neighbor to the left. So we call this the numerical stencil. Those are the 3 points that I need. Well, actually, it's these 2 points here that update the third one, right? And notice how the numerical stencil is one-sided. That's why this is called the upwind method. Because I know that the characteristic directions are moving to the right, right? The characteristic directions are like this. And my numerical stencil for this point, characteristics going through this point are coming in this direction. It's using the points that are in the direction of the characteristics, where they came from. So that's the upwind part of it. If I were using other points to the right, that would be looking downwind, right? Which isn't what we want to do. And it turns out that the method works, it's the one that works best because its stencil here, numerical stencil, is adapted to the characteristics in the problem. And in fact, if you choose your velocity and your Courant factor so that those characteristics exactly go like this, then you've got the exact solution with no error in it at all, right? And that's what you did when you set the CFL to 1 and used upwind. Okay? Well, when we get into more complicated problems, it's more difficult to figure out how to use the characteristic information. And, but there's a method called the Godunov method that does that for us. And let's sketch that out here. So in 1959, Godunov was a Russian scientist, and he invented this new method based on finite volume methods that uses the Riemann problem. The Riemann problem has all the characteristic information in it, right? When we talked about the Riemann problem, it was all about the characteristics. So the characteristics converging, we get a shock. If they're diverging, we get a refraction wave. If they're parallel, we get a contact discontinuity. The Riemann problem has all this nice characteristic information in it. So Riemann said basically, or Godunov basically said this. Imagine that I have my discrete grid. Let's see, I better have probably a lot of room here. Okay, I have a grid of points, and I have a function that I could plot like this. And remember we're using control. Godunov says, okay, we're going to use volumes here and not just finite differences. So he imagined having little cells that go in between the points. And what he said was, we're going to take the average value of the function inside of this cell. That's what we've been doing, right? We write that q is the integral of little q in x, right? I'm finding the average value and say it's right there. Okay. Now, one of his deep insights was, if I want to know if I want to use characteristic information and all of that kind of stuff, and I pretend that these functions now just are constant piecewise functions that are equal to the average value, this looks like a Riemann problem. And so he said, pretend that I have a Riemann problem right here and solve it exactly. And so he imagined having, here I have to draw multiple things all together. But imagine now I have characteristics. I have a shock moving this way, maybe a refraction wave moving that way, emanating from the Riemann problem at this interface. And I have to do that at every point. So I have another Riemann problem over here, and I will again have maybe a shock going that way and a refraction fan going like that. And at every interface here, I'm going to have some type of a Riemann problem. And I also have this contact discontinuity perhaps in there like this. Okay, and he said, basically, pretend that I've got a whole bunch of constant states, solve the Riemann problem in time. The Riemann problem in time, that tells me what the solution looks like at a later time, right? This in this characteristic diagram, this is time n. This is time n plus 1. Now, I know what the solution is at the advanced time. Simply do this integral again. Average the complicated Riemann solution out, and that gives me a new value for the average q at the new time. Okay? So his algorithm in 3 steps is, we write it as reconstruct, average or evolve, and finally average out. Okay? So I start off with the solution initially. I find its average value. I solve a Riemann problem in time. And then I have the exact solution for all these little Riemann problems. And I now average them out again to get the new average value at the next time. And then I just keep repeating that process. There's a Courant-like condition that arises because I can't have Riemann problem characteristics cross or I don't know what to do anymore. If these lines cross like this, then I don't know how to solve that anymore. And so I have to make sure that doesn't happen, and that gives me a Courant-like condition. And that's basically Godunov's method. It's very slow and time-consuming, though, because it's hard to solve the Riemann problem. And it's even harder to do all these integrals where these functions change. The Riemann problem has to be solved iteratively. Again, transcendental equations have to be solved numerically, and it's slow for fluid equations. But it was very nice because it automatically essentially has the upwinding in it for you. The characteristics in the problem are an integral part of the method. And so it automatically does upwinding. If the fluid's all moving to the right, you get the results all from the left and so on. Okay? If we come back over here, it turns out that you can really simplify and practice the algorithm. So what I've described right now, think back to those, Riemann problem solutions. I had a refraction wave, maybe a shock, and the velocity. Now imagine, integrating over this little region, the velocity, the pressure, the density, and it's a bit of work to find the value of the solution everywhere on that refraction fan. And then you integrate it all up, and it's almost like you did a whole bunch of work to figure out exactly what this functional form is, and then you just integrated it all to find an average. So it's like you did a whole bunch of work that you just threw away in the end. But fortunately, there's a way we can get around that. And that is by coming back to this equation that I've left up for the whole time. If you remember, this was the average value of Q at the advanced time. That's what Godunov was looking for, right? He was looking for the average values of these cells at the next time. That's written right here. This is the average value of those cells at the initial time. What are these? These were my numerical flux functions that I defined in terms of integrals in time. Right? Now, if we come back and look at this Riemann problem, let me draw it again here. So I had a Riemann problem. And I imagine I say I have a shot going one way. I have a refraction fan going like this. And then maybe I have a contact discontinuity that's somewhere. Anyway, somehow need to make that one different. Is that integral easy or hard to do for the Riemann problem? What do you think? Now remember that this integral is done at the interface, right? And it's an integral in time. If I look at the characteristic that comes from the interface and stays at precisely the same value in x, that's the dashed line that I've drawn here that goes vertically upwards, right? And then we look at the characteristic fans here, or the fan and the shock, whatever, discontinuity, and we see that actually the solution everywhere inside that, between those two waves, is constant. So this is an integral of a function that's constant in time. And that's what actually makes this work, is that this integral is actually easy to do. All I need to know is what is the solution. I still have to solve the Riemann problem, because I need to know where the fan is and where the contact discontinuity and the shock is. I mean, they could be, as I said before, they could have something more complicated like this, where everything goes off to the right or something. I still have to solve the Riemann problem to figure out exactly where those different features are, those different waves. But once I've found the answer, I can quickly evaluate the state that's at x equals, I plus a half. And then I'm done. And because this is a constant integral, or this is a constant function, the delta t here and the d, when I integrate in time, the time part cancels out. And I have something very simple. And I can then write this maybe in a slightly different way. Well, I'll just say here, the numerical flux function becomes simply f of, and people will write this as u star, right? Because star represents our solution to the Riemann problem, assuming the initial state was ui plus 1 and ui. So sometimes people will write it that way, that the numerical flux is simply the flux function in the PDE evaluated at the solution of a Riemann problem whose right and left states are those two. So this complicated integral here that was done in the numerical flux, I actually don't have to do. And so that's what makes this method work out. This is really a big advance, and all the fluid methods, well, almost all of the fluid methods that we use today for compressible fluids with shocks are based one way or the other on Godunov's method. Godunov's method is still a very dissipative method. It's a first order method. So it's like upwind. In fact, if you do Godunov's method for an advection equation, it just turns into upwind, the upwind method. But we have some things we can do to improve Godunov's method. Okay, and we'll talk about those. Since we have just a couple minutes, I don't really want to start anything new, but let me just give you a taste of what will come. So Godunov's method is the error, and Godunov's method is order delta t, delta x. As I said yesterday, you'd never win if your error doesn't improve as you work harder. Okay, or, doesn't improve faster than the extra work you have to do. And so we would like to improve that. Can you think of anything that we could do to improve maybe our solution? Well, we go back to these steps and we can imagine what we can do to improve things. For one thing, maybe we don't assume that these initial states are constant straight lines, but maybe we assume that they are straight lines, linear, or quadratic functions, parabolas. We could fit parabolas or straight lines to this. And that may give us better accuracy, and in fact it does. And so that's one of the things we'll talk about tomorrow as we talk about how to improve this to get to actually the order accuracy level we need. We will start, instead of using the straight lines Godunov has, we'll start using straight lines. I'm sorry, instead of using constant states, we'll use linearly reconstructed states. So Godunov constructed with zero order reconstruction or constant states. Maybe we can use linear order reconstruction, straight lines, or second order, third order. If you go to E&O schemes, you'll see even fifth order schemes and eighth order schemes, and so you can go crazy. Another problem with Godunov's method is solving the Riemann problem is still hard. Now, I said that this flux integral kind of saves us because it's an integral at a single point in space and time where the solution is constant. It's still hard it can still be difficult to solve. It's time consuming. We want something that works a little bit faster. And so I'll just write here to improve things, we're going to consider next higher order reconstructions. And again, with the Riemann problem, it's expensive to solve, and we're using only one single point that comes out of it. And so maybe it's possible to approximate the solution, not find the full solution of the Riemann problem, but find an approximate solution. And that's the other thing we'll look at, are using approximate Riemann solvers. Since we're only going to take one point from it anyway, if we get an approximate solution, maybe it's good enough. And those are the two things that we'll look at tomorrow to come up with the high-resolution shot capturing methods that we use today in the research level codes for numerical relativity. The averaging step, luckily, is taken care of us by the numerical flux, and so there's nothing really to fix there. Okay? Any questions?
Sir,
Mm-hmm.
suppose their contact discontinuity is on the same side of the that characteristic line.
So it's right on top of the characteristic line?
The same side.
Uh-huh.
Then the function will not be constant on that.
Yes, then it's an ambiguous case, and it turns out that that will only happen if the two states have the same initial state. So the contact discontinuity will only be a line straight up and down if the two initial states are the same. And then you just, then the answer, then it doesn't matter, it's just going to be, the evolution doesn't occur if the states are constant, and so it's just the value of the flux evaluated with the state. And I don't know if I said that well enough, but I think you got what I mean. Uh-huh.
I did not follow how you're solving this integral.
Okay, so this integral here, this is an integral in time of the flux function with the solution at the midpoint, xi plus a half. And it could vary in time, right? And so then we came to Godunov's technique here. And remember, these are the points I, xi plus 1. The midpoint here is this xi plus a half. This is the point, so this halfway point, this boundary between the two cells is where the Riemann problem is assumed to, the center of the Riemann problem. And so when I look at the characteristics that come out, they will propagate, or they will be, some type of a fan around here. But this integral is just the value of the flux along the straight line in time, or that's all I'm integrating. I guess I should draw it here, but so I'm integrating just along that line, and the solution is constant along that line. It doesn't change, and so I can just write it in this way without the integral.
What about the fan?
So the fan will always be moving one other way. If the fan is over here, I mean, I could have a case where the fan does this, and the shock is over here, or I don't know, whatever. But the point, when I integrate above where the initial discontinuity is, the solution is constant in time. Because all of the lines that I draw here originate here, and they go off in one direction or another. And so I will only have a characteristic along this axis if both states are initially the same. And so I always have a constant state along that line. Okay, any other questions? Okay, well, thank you.